Celsius. And what is observed in this case is that more or less below minus 20 degrees Celsius, the water turns into ice, and that's all, that's it, okay? At around minus 30 degrees Celsius, the water turns completely into ice, and then there is a lot of cracks that appears like that. Suddenly, once the water was completely turned into ice, you have this pattern of cracks. And above, around 40 degrees Celsius and above, you have this kind of pattern. And this is somewhat strange, because you know the temperature is decreasing, it means the load is increasing, it means that you have more and more energy, but finally you consume more energy here than here, okay? So we will try to explain this paradox using the couples criterion. And to do that, we haven't used the geometry that of the water drop and the ice pancake. We have used a linear model we have already used for multi-cracking of thin films deposited on the substrate. But just consider this layer like that. Okay, we have just considered this problem where the substrate here at the given temperature, and here the ice layer is growing, okay, and above you have water. It could be, and you see that, for instance, the ice thickness is identical to time. So we don't need to describe the evolution with respect to time. We have just to describe the evolution of the problem with respect to the ice thickness. Okay, and it could be, and answer to Raoul's, the question of Raoul this morning. In this case, you have an external mechanism that is the water that is turning into ice, and this is growing, and you consider the property of ice, and of course you have to know how this thickness evolves. But in our case, it's not necessary. We try to have some properties of ice in the literature, and you see we get something quite strange because 10, no 10 point something, no 10, 1. It's quite approximate, but indeed there is a big discrepancy, a big scattering in the properties of ice. This is the simplified evolution of the temperature through the thickness. This is, here you have the time, here you have the temperature. At the very beginning, okay, the ice layer is very thin, and then you have a gradient of temperature from Tc along the plate to 0 degrees Celsius, I mean T0 here, at the interface between ice and water. It is the temperature at which water turns into ice. And then the thickness of the layer, of the ice layer increases, okay? And at the time, it's completely turned into ice. But at that time, there's still a gradient, because this is at the temperature of the plate, and this is at the temperature of the interface where the water turns into ice. And then the temperature decreases, I always use it decreases, and finally you get a uniform temperature into the ice layer. Okay, so we have the parameters. We can try to use the coupled criteria. This is obtained for a temperature of minus 20 degrees Celsius. Okay, fortunately the figure is here. You have the blue line is the stress condition. This one is the energy condition, G incremental, and this is G. But indeed, we ignore G. Okay, so you see that for minus 20 degrees Celsius, we have an initiation at this length, more or less when the water has turned into ice more or less completely. Okay? If we consider minus 30 degrees, of course the layer, the ice thickness is smaller, And again, the blue line is the stress, this is the energy condition, and we have a solution here, okay? And now if we move at the temperature minus 40, okay, the layer, the ice thickness is smaller, but we still have a solution. And finally, if we put that on a plot, what we get is, okay, what was expected is that finally the ice formation, the distance between cracks during ice formation decreases when the temperature decreases, I mean when the load increases. But of course the paradox is not solved at all, because remember the paradox, finally we have something like that, but for minus 30 degrees we have a very, very tight pattern of cracks. So we will try to change, and what we have to find is to find a mechanism that inhibits rupture until temperature reaches minus 30 degrees Celsius. So the rupture is delayed, should be delayed for this temperature in order to permit, we know that it's the stress conditions that allow this inhibition, and we have selected sigma c instead of value 1 proposed in the table. We have selected sigma c equal to this value. This value corresponds to the tensile stress that exists in the ice layer without any crack. It's just the thermal residual stresses that exist in the ice layer when the ice is at this temperature. Okay? So we have selected this value for sigma c. And then what happens? Now again we consider the temperature minus 20 degrees Celsius. Minus 10 degrees Celsius, we wait a long time, the temperature is homogeneous through the ice layer, the stress is homogeneous through the ice layer, but it is smaller than 1. Sigma c is smaller, sigma is smaller than sigma c. So, okay, this is the energy condition, this is the stress condition. Here you see there is no match, okay? So, nothing can occur. Let us now consider the temperature T equal to minus 30 degrees Celsius, but just the water is just forming to turn into ice. It means that the temperature here along the interface is minus 30 degrees, and here it is 0 degree, because it is just the interface between water and ice that has finished. Okay? Then this means that the stress here is around 17, as we have selected, but here at the surface is still 0. Okay? Then, now we can consider, we wait a long time, and then at minus 30 degrees Celsius, the water has turned completely to ice, and the temperature now is homogeneous into the thickness of the ice layer. And then it means that the stress condition is here. It means that the stress condition is fulfilled. The stress condition is fulfilled. This is the energy condition, and this gives us the solution for this case. Okay, with a rather small crack spacing. And if we go on and calculate for other values, if temperature is larger than minus 20, I mean warm temperature, there is no crack. At temperature of minus 30 degrees Celsius, it was the hinge, the temperature hinge detected by the experiments. And from this temperature we have derived the value of sigma c, and for this temperature we get that point here. You mean a very tight, small distance between cracks, because in our model it's just a simple model. The cracks are close to each other here, and then now if we try to do calculations for smaller temperature, I mean for instance minus 35, minus 40, and you see that finally at minus 30 degrees Celsius you have very close crack, but next you have a large crack pattern, of course, that slowly increases when the temperature is lower and lower. So I think that we have solved the paradox.
We have time for some questions. If there are any, please go ahead. Yeah, please go ahead.
Do you consider it possible that water ice has a defect population that depends on the solidification speed for undercooling?
Of course, the large scattering, there are many defects in ice. But you see, in this case, it is going very quickly. It is, the water turns into ice very quickly. I think that between the time the drop of water reaches the plate and it is completely turned into ice, and the temperature is homogeneous, it's around 1 second. It goes very fast because the thickness, the final thickness of the layer is 150 micrometers. It's quite small, so it goes very fast. Is there some defect? We don't know. We know that in ice there is a lot, of course, if you consider ice from the sea or ice from the river. And this is probably the reason why the table was just approximate values. That if there is defects, of course, it can change many things.
The last, and I might have totally agree, this figure reminds me to the thermal shock cooling. This is a typical patterns. So for instance, if in geotechnique Haddad columns say solidificate, you have to say the temperature gradient, and then the cracks form in a pattern which minimizes the energy. Or thermal shocking or drying of mud, you have exactly this pattern. So the transient temperature through the height of the this drives the crack. From where come the stresses from? If you have homogenized temperature, then there's no stress in it.
Yeah, no. In case of a column, here you have stresses because the plate doesn't deform to the temperature. So the ice is stick on the plate and it cannot stretch. So you have the water trying to shrink. Sorry, not to shrink, and then it is in tension because it is.
Ice is extending. Changes from water to ice.
No, shrink because it's colder and colder temperature. So it shrinks.
After it's nucleated, the phase transformation will induce tensile stresses due to phase transformation due to expansion. There's no phase transformation in the ice.
Maybe we can discuss that later on. There is another question, and we want to be on time. I'm sorry that I have to interrupt the discussion, but we want short questions and short answers, please. We have this 15 minutes.